Okay. Actually, in this example, instead of starting with a probability model in terms of regular probabilities, I'm actually going to define the model in terms of conditional probabilities, and we'll see how this is done. So here's the story. There may be an airplane flying up in the sky, in a particular sector of the sky that you are watching. Sometimes there is one, sometimes there isn't, and from experience you know that when you look up, there's 5% probability that the plane is flying above there, and 95% probability that there's no plane up there. So event A is the event that the plane is flying out there. Now you bought this wonderful radar that looks up, and you're told in the manufacturer's specs that if there is a plane out there, your radar is going to register something, a blip on the screen, with probability 99%. And it will not register anything with probability 1%. So this particular part of the picture is a self-contained probability model of what your radar does in a world where a plane is out there. So I'm telling you that a plane is out there. So we're now dealing with conditional probabilities because I gave you some particular information. Given this information that the plane is out there, that's how your radar is going to behave. With probability 99% is going to detect it, with probability 1% is going to miss it. So this piece of the picture is a self-contained probability model. The probabilities add up to 1, but it's a piece of a larger model. Similarly, there's the other possibility. Maybe a plane is not up there, and the manufacturer specs tell you something about false alarms. A false alarm is the situation where the plane is not there, but for some reason your radar picked up some noise or whatever and shows a blip on the screen. And suppose that this happens with probability 10%, whereas with probability 9%, your radar gives the correct answer. So this is a sort of a model of what's going to happen with respect to both the plane. We're given probabilities about this, and we're given probabilities about how the radar behaves. So here I have indirectly specified the probability law in our model by starting with conditional probabilities as opposed to starting with ordinary probabilities. Can we derive ordinary probability starting from the conditional ones? Yeah, we certainly can. Let's look at this event, A intersection B, which is the event up here. That there is a plane and our radar picks it up. How can we calculate this probability? Well, we use the definition of conditional probabilities, and this is the probability of A times the conditional probability of B given A. So it's 0.05 times 0.99, and the answer, in case you care, it's 0.0495. Okay, so we can calculate probabilities of final outcomes, which are the leaves of the tree, by using the probabilities that we have along the branches of the tree. So essentially what we ended up doing was to multiply the probability of this branch times the probability of that branch. Now, how about the answer to this question? What is the probability that our radar is going to register something? Okay, this is an event that can happen in multiple ways. It's the event that consists of this outcome. There is a plane and the radar registers something, together with this outcome. There is no plane, but the radar still registers something. So to find the probability of this event, we need to add the individual probabilities of the two outcomes, of these two outcomes. For the first outcome, we already calculated it. For the second outcome, the probability that this happens is going to be this probability, 95%, times 0.10, which is the conditional probability of taking this branch, given that there was no plane out there. So we just add the numbers, 0.05 times 0.99 plus 0.95 times 0.1. And the final answer is 0.1445. Okay, and now here's the interesting question. Given that your radar recorded something, how likely is it that there is an airplane up there? Your radar registers something that can be caused by two things. Either there's a plane there and your radar did its job, or there was nothing but your radar fired a false alarm. What's the probability that this is the case as opposed to that being the case? Okay, the intuitive shortcut would be that it should be the probability, you look at the relative odds of these two elements and you use them to find out how much more likely it is to be there as opposed to being there. But instead of doing this, let's just write down the definition and just use it. It's the probability of A and B happening divided by the probability of B. This is just our definition of conditional probabilities. Now, we have already found the numerator. We have already calculated the denominator. So we take the ratio of these two numbers, and we find the final answer, which is 0.34.